Welcome. In this video, I'm going to demonstrate how to evaluate this integral using a trigonometric substitution. And there are three cases. And the thing to look for, I feel, is what sign is this? Well, this is positive, so that we don't have to distinguish between the two because there are two cases with a negative sign. So what this tells us is that we need to let x equal. So what we want is we want x to equal a tangent theta. Well, what is a? Well, we have 4 plus x squared. This is 2 squared plus x squared. So that tells me a equals 2. So let x equal 2 tangent theta. That will be our substitution. Well, what that tells me is that dx here, so that's the derivative of x with respect to theta. We're using implicit differentiation. Well, that's equal to 2 secant squared theta. And if you notice, I'm doing this in erasable ink, so to speak, mostly as a reminder that this is where the d theta here comes from. We multiply both sides by d theta to get rid of this one. So this is how we end up with dx equals 2 secant squared theta d theta. Okay, so now we can make our substitutions. So everywhere I see an x, so it's in two places here and here, I'm going to replace that with this x. So what does that look like? That looks like, well, let's start with our denominator here. This x here is going to become 2 tangent theta, and then of course I square it, and then we have our square root with 4 plus, again another x, so 2 tangent theta squared. And then in my numerator here, I'm going to replace what would have been a dx. I'm going to replace that with 2 secant squared theta d theta. Well, let's just clean this up a little bit. So what we actually have is we have the integral of 2 secant squared theta d theta here in our numerator. And in the denominator, we have 4 tangent squared theta times the square root of 4 plus 4 tangent squared theta. 2 over 4 is 1/2, so that's nice. I can bring that constant of 1/2 out to the front. And then in my numerator, it's going to stay the same. So every step, just write down the same thing. Whatever you're not actually working with should just be written down every step. And in the denominator, I have tangent squared theta. But then in the square root, I have 4. And notice they both have a 4 in common, so I can factor that 4 out. Well, what's 4 divided by 4? That's 1. And then to that, I'm going to add this divided by 4, which is just tangent squared theta. We have a 1 plus tangent squared theta. That's equal to secant squared theta. This is just one of 3 Pythagorean identities that all can be derived from the identity cosine squared theta plus sine squared theta equals 1. And I'm not going to go over how to do that here. So let's continue. I have 1/2 times the integral, and let's start with the denominator since it's more interesting. Well, the square root of 4, that's just going to be 2. So let me bring that constant out to the front. And actually, so you know where it came from, I'm going to make it orange. And I'm going to make this 4 orange. Okay, so that's where that 4 came from, or excuse me, that 2 outside of the radical. In my denominator, then I have tangent squared theta, and then this here is just the square root of secant squared theta, and in my numerator, I have secant squared theta d theta, so this is 1 over 4 times the integral of secant squared theta over tangent squared theta d theta. Oh, excuse me. I left space here and forgot to write it down. I should have a secant theta there. So this is 1 over 4 times the integral of secant theta d theta over tangent squared theta. And this is where we just need to use some trigonometry. What I mean is, so secant theta is 1 over cosine theta, so that's one trigonometric identity. And tangent theta, well, that's sine over cosine, and I have a tangent squared theta, so this is sine squared theta over cosine squared theta. And this gives me 1 over cosine theta times cosine squared theta over sine squared theta. So as you can see, we will just end up with, in our integrand, the constant out front times the integral of cosine theta over sine squared theta d theta. So let's pause here and reconvene, or not really reconvene, show where we're at in this process. We've already done one substitution, and that's literally you're changing the variables. So we changed the variables from x to theta. Now we need to do this again. So this is our second substitution here. And we're going to let w equal sine theta. So these tend to be called u subs. I prefer to use a w. So it's just a straightforward substitution, u sub with a w. So dw, apologize for that little jump in the screen there, dw equals cosine theta d theta. And that's right here. So we really have, let's go in this direction here, 1/4 of the integral of 1 over w squared dw. Well, what is this equal to? This is equal to negative 1 over w. Oh, excuse me, I forgot that constant before. Negative 1 over 4w plus a constant. And so we have w's here, but we started with x's. So the first thing we need to do is undo the most recent substitution here. So this w is actually sine theta. So I should have a sine theta in that denominator. So let's undo 2 to get negative 1/4 times 1 over sine theta plus a constant. Okay, so we've undone 2. Okay, let's undo 1 now. So this is a little trickier, so let's undo the first change of variables. And so for that, we need to use this fact here. We know x equals 2 tangent theta. So tangent theta equals x over 2. And now I can sketch a triangle here. This angle is theta. Well, we know tangent is, not adjacent, it's opposite adjacent. So that tells me that the opposite side is x, the adjacent side is 2. And now I can use this to find sine theta. So sine of this angle is going to be opposite over hypotenuse. Well, what is the hypotenuse? Using the Pythagorean theorem here, to get h, we end up with h squared equals 2 squared plus x squared. So really, h is just equal to the square root of 4 plus x squared. And I'm using the erasable pen on purpose since I'm running out of space here. So h is equal to the square root of 4 plus x squared. And actually, let me just move that over here to save space. Quickly observe that what we started with, 4 plus x squared in our radical, is exactly what we end up with when we solve our triangle. So look out for that. What does sine theta equal? It's opposite hypotenuse, so it's x over the square root of 4 plus x squared. And our sine theta here happens to be in the denominator, so that tells me that 1 over sine theta is equal to the square root of 4 plus x squared over x. So now we can undo 1 to get negative square root of 4 plus x squared in our numerator, and in the denominator that's divided by 4x, and then plus our constant. So all of this work here is to show that this integral is equal to negative square root of 4 plus x squared over 4x plus c. I hope this video has been helpful.